Alright, go ahead and get started. So this is homework 10. This is the last homework of the class. You guys just took the last mini term on Monday, yesterday. And this homework is required for those of you that are hoping to skip the final. And for those of you that are planning to take the final, I'd still recommend doing this homework, as this is a great way to review for it. Because this one goes over virtually everything that's important that's been covered in the class. So I'm just going to jump into it. It's really just one problem, but it goes to part J. So that's one way to think of it. All right. So looking through this. So MN Chemicals, always on the cutting edge of catalysis and reactor engineering, has developed a new catalyst recovering dirt, D, to cash, C. When dirt is in the presence of the new catalyst along with water, W, it converts it to cash. Note that the cost of the catalyst is much less than the cash produced from it. The catalyst has a total number of sites, CT. Heterogeneous catalyzed mechanism is shown below. Represents open binding sites on the catalyst surface. Assume that the stoichiometric numbers for each step are 1. Okay, there's our mechanism. We have 3 QE steps and 1 irreversible step. And we said that for all is equal to 1. So that'll make that easier for us. Okay, so moving on to part A. Draw an arrow diagram for this reaction, showing the relative rates of each step in the mechanism. This one is a pretty easy one. I'm not going to actually draw it. I'm just kind of show the basics. So remember that your rate determining step, your R net, is represented by this shorter line. Give me 1 second. What was that? Okay, sorry. I heard a loud noise, and I think my cat broke something. But that's for later. Okay, so we have our arrow diagram where our R net is represented by this dotted line here, and remember that we have 3 QE steps. And QE represents that the reactions are going so fast in both directions that they are essentially equal. And they are going so much faster than the actual rate determining step. And remember that the rate determining step is as fast as R net. So you'll draw the arrow diagram based off of that. And then moving on to, I'll leave part A up to you guys. Part B, a little bit more difficult. What is the overall rate of reaction expressed in terms of quantities that are easily measured and the equilibrium and rate constants? Okay, so first we have to decide what our rate determining step is. And if you're remembering back to when we did not just catalytic mechanisms, but just normal mechanisms without the catalyst, we said that in a mechanism, that if there is an irreversible step in the mechanism, the rate determining step will always be irreversible. So going back up to our mechanisms, we have 3 QE steps and 1 single irreversible step. So step 3, this guy right here, that is our rate determining step. All right, so can say that R is equal to R3. R3 is just equal to KR times our D star times our W star. And then since we have two surface reactants, or surface species, we have to divide by the CT. And if we only had one, we wouldn't have to divide. Let's say we had three surface species, we would have to divide by CT squared. Okay, so now we need to do this in terms of easily measurable quantities and equilibrium rates. So D star, W star, they are not easily measurable. So we'll have to find different expressions for them. So from remembering that our first, second, and third steps are QE, from step 1, we can get that D star is equal to our capital KD times D times star. Same thing for our W star from step 2. All right, then going and plugging that in. Man. Of course, over CT. All right, now we've still got the our star term, our empty sites. We still need to get rid of that. So in order to do that, we will do a site balance. And we know almost everything here. We don't know C star, so we'll get C star in terms of the other quantities using our fourth step, which is also QE. And we'll get that C, oh man. And then plugging it in. Oh man. That's supposed to be a star. Okay. Now we can solve directly for our star term to get and we plug this back in to our reaction rate right here. We'll get and there you go. So that's our overall reaction rate. So moving on to part C. There we go. If star is massy, what is the overall reaction rate? So when we assume massy, so I'm just going to write out the whole site balance. Good Lord. There we go. So when we assume massy, we assume that whatever is massy, in this case, this guy, we assume that the concentration of that is so large in comparison to everything else that they essentially go to 0. So we get that CT is just equal to our empty sites. And then from there, we solve for R. And I'll leave that to you guys. It's not too terribly difficult. Okay, part D. Given that 20% of the way into the catalyst particle from the surface, the concentration of D is 1/10, is 1/10 of the value at the surface. What is the internal effectiveness factor of the system? Assume that the reactor is first order in D and 0 order in W. So with that first one, the last sentence here, assume the reactor is first order in D, 0 order in W, this is saying assume first order system. So, as you saw before, that we're looking at within a certain distance into the particle, we're going to have a different concentration than on the surface. So that kind of goes back to our concentration profiles and this fancy little xi term, which, if you'll recall, is equal to Ca over Cas, our surface concentration, which, when we assume it's first order, we can get this. Where our lambda is R over capital R, where capital R is the radius of the catalyst and little r is a certain distance in. So we're told that 20% of the way into the catalyst, the concentration of D is 1/10 the value at the surface. So we are 20% of the way into the catalyst, which means that we are 80% of the way to the surface, which is one way of saying that 1 minus, minus 0.2 times capital R over R, because we're 20% of the way into the catalyst, 20% of the way into the surface. So that's going to essentially be equal to 0.8. And we said at this location that the concentration is 1/10 the value at the surface. So we'll say that Ca over Cas, you can rewrite as 1/10 Cas over Cas, which of course just equals 1/10. So you'll get that xi is equal to 1/10, which is equal to 1 over 0.8 times hyperbolic sine of 0.8 times the Thiele modulus over hyperbolic sine of the Thiele modulus. And then you're going to use some sort of solver to solve for the Thiele modulus. And based on what you get, based on that, you will use one of these equations here, particularly these last two down here, to find the internal effectiveness factor. So if your Thiele modulus is, say, 30, you could use this last one down here, where your internal effectiveness factor is just 3 over, the Thiele modulus. If it's somewhere between 2 and 20, you'll want to use that first one, that 3 over Thiele modulus squared times Thiele modulus minus 1. So based on whatever you get, will tell you what equation you want to use for the internal effectiveness factor. Okay, moving on to part E. Give me a sec. Okay, so we got due to high internal mass transfer limitations on the system, researchers at MN Chemicals have decided that a heterogeneous system was not the best path forward for the system. They decided to work on a new reaction system to convert dirt to cash. At moderate pressure and a significant amount of heat, they can gasify the dirt to form cash. The reaction proceeds as a first-order reaction in D. Water is not necessary for this reaction. However, a side product, carbon monoxide, CO, is also produced. The reaction is listed below. Okay, so assume all substances are ideal gases. Part E, when a PFR reactor with a jacketed heat exchanger is run under isothermal and isobaric conditions at 700 Kelvin, what reaction volume is needed to achieve a conversion of 60%? Assume first order rate constant is 700K, at 700K is 0.1 per second. Activation energy is 5,000 joules per mole. The feed is pure gasified dirt. The specific heat capacity is 34, which is constant over all temperatures. The volumetric flow rate is 700 Kelvin. Okay. That tells us what we need. So for part E, we know we have a PFR. So let's just preemptively write the PFR design equation. This is something you guys should hopefully have committed to memory. It's an important one to know. We have said that the reaction proceeds as a first order reaction in D, which means that we can write minus RA, I guess, just as our rate constant times D, our concentration of D. So, what am I trying to find again? Oh, we need the reactor volume. Okay, sorry. Okay, so now we need to write our concentration of D. And remember, this goes back to that full equation where we have Ca naught. And remember, A is just something to signify the limiting reactant. In this case, it's going to be D because it's our only reactant. Times theta A minus nu I over nu A times XA over 1 plus epsilon XA times T naught over T times P over P naught. Okay, we are told for this particular step that we're doing, we are isothermal and isobaric. So that term goes to 1, that term also goes to 1. Again, that little subscript A is just signifying the limiting reactant. In this case, D is the only reactant, so it's by default limiting, which makes theta A equal to 1, and this ratio of the nus also equal to 1. Epsilon, remember it's delta times YA naught. YA naught, again, we only have pure gasified dirt coming in, so YA naught is equal to 1. I'm pretty sure it just said that. Dirt to form ash. Yeah, the feed is pure gasified dirt. Okay, so our YA naught is equal to 1. Delta, remember, is equal to our nu I over nu A. So that's going to be equal to, so we have nu A is equal to 1, so we've got our 0.2 over 1 plus 1 over 1 minus 1. That's going to just be equal to 0.2, which makes epsilon equal to 0.2, which makes our concentration of D equal to our, I'll write it this way, concentration of D naught, that's just our initial concentration, times 1 minus XA over 1 plus 0.2 XA. Okay, so going back to the design equation, V is equal to FA naught times 0 XA times DXA over D naught times 1 minus XA over 1 plus 0.2 XA times K, sorry. That's just concentration. Remember, it's the whole reaction rate. So, rearranging some things. Let me move this down. I'm not very spatially intelligent. So there's that. All right, what terms do we still need to get for this problem? So we're told K. We're given K, assume the reaction 700 Kelvin, 0.1 seconds. We're given K. Are we told anything about the molar flow rate, or FA naught, or D naught? We're not. But we are given the volumetric flow rate. 5 liters per second. So we can write that, and if you'll remember that FA naught over D naught moles per second is equal to V naught. So we can, once again, simplify over K. So there's that. And if you recall that we're trying to find the volume to get a conversion of 60%. So now we know everything we need to know. Now we just have to integrate. So our volume is 0.6. And there you go. That's the equation that needs to be solved. All right, moving on to part F, I believe. Yes. Okay. Qualitatively, how does this conversion compare with that calculated by the segregation model? Just give me a second here. I can make sure I answer this right. So, compared with the segregation model, if we go back to the design equation, the final design equation that we obtained, we can see that it is independent of temperature. I mean, not temperature, sorry, concentration. which is true for a first order reaction. The segregation model of mixing and mixing as a whole is something that affects concentration. And if concentration does not show up in this design equation, then we can expect that the conversion for the segregation model will be the same as the one that was previously found. So mixing directly affects, I don't know if I'm using the right effects, concentration. Since concentration is not important here, the conversion of the segregation model will be the same. And this only holds true for a first order system. Okay, so moving on to part G. What is the highest conversion possible if the reaction is assumed to be reversible? The equilibrium constant is 8 moles per liter to 0.2 at 700 Kelvin. Okay, if you'll remember that our equilibrium constant, just capital K, is equal to products over reactants, where they are to the power, or products and reactants are to the power of their stoichiometric number, or stoichiometric coefficient. So, from the equation, if it will load, there we go. From the reaction, we can write our equilibrium conversion in terms of those concentrations. So we have capital K is equal to C times concentration of CO to the 0.2 over concentration of D. And remember, we're still in a gas phase reaction, so we still have to consider our epsilon and our temperature and pressure changes. In this case, I think we're still basing it off of the conditions in part E. So we're still isothermal. We are still isobaric. We know what the concentration of D is. It is D naught concentration of C. And we'll find that going back up here using this equation that I've so nicely scribbled out all over the place, where the concentration, we'll still use the initial concentration of D. Theta of C, in this case, is going to be 0 because there's no C coming in. The ratio of the nus is going to be 1 because for C and D, it's 1 to 1. Epsilon remains the same, 0.2. So we can get the concentration of C is equal to D naught times XA over 1 plus, 0.2 XA. And for the C naught, same thing, sorta. We have the D naught. Theta for CO is 0 because it's pure D coming in. The ratio of the nus, in this case, is 0.2 over 1. So we multiply that by 0.2 XA. Or 0.2 over negative 1. Those will cancel out the negatives. And then same epsilon. So that's what we get for C naught. So now we can plug those back in. We know that our equilibrium constant is equal to 8 moles per liter to 0.2. So I'm plugging in for C right now. Plugging in for CO. And plugging in for D. All right. Do we know D naught? We don't. In the last problem, we ended up just getting rid of the constant of any concentrations. But we can find D naught because, again, if you'll recall, all substances are ideal gases. We are given a pressure. We are given a temperature. That guy right there, 700 Kelvin. So, going back to the ideal gas law, our best friend, P equals R over T. Since it's pure D coming in, we don't have to worry about dividing or multiplying by any gas fractions. And I'll probably just leave it there. You guys can do that math. That's not terrible. So you can calculate D naught using the ideal gas law, and from there, now you only have one unknown, just XA. Solve for XA. And that will give you your equilibrium conversion. I recommend using maybe like Excel or Python for that. A little hard to do by hand. Okay, moving on to part H. If the heat of reaction is 5,000 joules per mole for all temperatures, what is the maximum heat load on the heat exchanger? Okay. So we're trying to find the maximum heat load on the heat exchanger, or the Q value. And we know Q is going to be in units of watts, or kilowatts, same thing, or joules per second. So, doing some quick unit stuff, we know that the heat of reaction is going to release, it's releasing minus 5,000 joules per mole, but it's going to be absorbed by the heat exchanger, so negative delta HR. This is the heat times the flow rate of D, initial flow rate, molar flow rate of D, times the conversion of D, will give us the amount of energy produced from the reaction. And the amount of energy produced from the reaction is going to be equal to the amount of energy removed by the heat exchanger. Just to be clear, XD is, it can be from either part E or part G, I believe, but I think he initially wrote it with the intention of XD is equal to 60%. We go back to use irreversible. Conversion. So that's just kind of a simple little energy balance where the heat produced from the reaction is going to be the heat that is going to be the heat load of the heat exchanger, the amount of heat the heat exchanger needs to remove. So moving on to part I. Part I. There's a problem with the heat exchanger which causes it to completely fail. The reaction is very well insulated. What is the temperature and conversion at the outlet of the reactor? Use the same value calculated in part E. Assume that the reaction is irreversible again. What would the volume have to be operating in adiabatic mode to reach 75% conversion? Okay, so we are now no longer operating adiabatically. Not adiabatically, isothermally. But this sentence right here, the reactor is very well insulated, that is code word for adiabatic. No heat is leaving the system. So, now that we're operating non-isothermally, let's do the energy balance for this guy. So I write out the entire energy balance, if I can remember it. I hope that's it. Yeah, I hope I got it all. Oh, this isn't the one. Okay. So, we are almost always operating in steady state. There's no shaft work, and we have said that there is no, that is adiabatic. So Q, by that logic, is equal to 0. Remembering back a little bit farther, we have said that delta HR is equal to delta HR at a reference temperature minus delta CP times T minus TR. Before, well, I'll just keep going and show you. And then, I forgot something. T minus T naught minus FA naught XA delta HR. Okay, now I hope I have it all. Yes, I do. Good. Okay. So, and this is our definition for delta HR. We now know that the FA naughts can cancel because we have set everything else equal to 0. We can solve for the temperature to be of this form. If we solve for temperature based off what we have here. So some of you might remember this form. This is very close to what I just wrote down. So we used this before for adiabatic systems, the second one here. The reason why we're using this, we're going to have to use this top one up here, is because that this bottom one is only true if delta CP is equal to 0. And if you're going to find in this problem, delta CP is not actually equal to 0. So going back up here, let's solve for that real quick. The feed is pure gasified dirt. Specific heat capacities of all substances is 35 joules per mole Kelvin, which is constant over all temperatures. So I'm just going to say, since they're all the same, I'm just going to say that I'm just going to call it CP. So we know that delta CP is equal to the sum of nu I over nu A times CP. And again, A is just the limiting reactant. So, and again, since it's all they're all the same, I'm just going to call it CP and remove it. So let's do it for C. So for C, it was just 1 over 1. For the CO, it was 0.2 over 1. And for D, it's 1 over 1. So the ones cancel out, and you get that delta CP is equal to 0.2 CP on 0. So, which is why we need to use this top one up here, not the bottom one, which looks a little nicer. Okay, solving for the other term that we don't really know, our theta I, CPI. So we got theta D, CP. And again, I'm just writing CP because they are all the same. Theta C, CP plus theta CO, CP. It's pure D coming in. Theta D for the theta for the limiting reactant is always 1. Theta C, 0. Theta CO, 0. So it's just equal to CP. Cancels out, nice. So plugging in what we know into there, so we have X, negative delta HR. This negative delta HR is just the 5,000 that we were given earlier, plus CPT naught plus XA TR times 0.2 CP over CP plus X times 0.2 CP. This TR, that TR depends on the temperature that our values were given at. In this case, we can say that the reference temperature is just, I want to say just 700 Kelvin. I believe so. It says for all temperatures. Yes. It should be fine for 700 Kelvin. I guess I can check mine to make sure. That's what I did. Yeah, 700 Kelvin should work. Okay, so moving on. Going back, so here is our energy balance. Moving to the mass balance. We can use the same equation that we used before. Almost. So, kind of this guy right here. We'll use something similar, but if you'll remember now, when we did that, we said that we were isothermal. But we are adiabatic right now. I mean, yeah, adiabatic. So, non-isothermal. So, the only thing that's going to change there is our expression for the concentration of D. So that is going to be of the form XA over 1 plus 0.2 XA times T naught over T. Right? Because we're non-isothermal, we have to include this part. I'm going to write the energy balance in the form that will, the mass balance in the form that we're going to need it. dV over dx. Are we trying to sign for volume? Or we're trying for conversion. Okay, other way. Is just equal to our reaction rate over our molar flow rate, which we can write out to be K times D naught times 1 minus XA over 1 plus 0.2 XA times FA naught, or FD naught, I guess, times T naught over T. Before, we just used the volumetric flow rate instead of using the concentration and the molar flow rate, but by this point you should already know those values. And then the other term that we need to care about, concentration, initial concentration, initial molar flow rate, that won't change as a function of T. Obviously T is going to change. We already found an expression for T. T naught, not going to change, but K is going to change with T. So how will K change with T? It's going to be of this form. This fancy Arrhenius equation. This doesn't go away either. So, this right here is the mass balance that you need to solve. This up here is the energy balance that you need to solve. You need to solve both of those simultaneously in order to get your conversion and your temperature. And I'm not going to do this one in Python. I think you guys have done similar to this before, so it won't be hard. I don't think it'll be too difficult to go change code that you've used before in order to solve for this. So that solves for the first part, and then using the same volume calculated in part E, assume that the reactor, what would the volume of the reactor have to be operating in adiabatic mode to reach 75% conversion? Okay, so I'll give you a quick little hint. When you're integrating this, you're going to integrate from V is equal to 0 to V is equal to 49 liters, and only care about the last point. And the last part asked for what is the volume in order to get a conversion of 75%. In order to do that, you're just going to flip everything. So we want volume as a function of dx, which is going to be equal to FA naught over K times the concentration of D. So you're going to flip all this stuff over here. Back up more. There we go. So yeah, you're going to flip all that stuff there in order to get it to match down here. K is still the same. T will still be the same. They're just now in different places. And in order to do this, you're going to integrate from x is equal to 0 to x is equal to 0.75. And again, I only care about the last point. There you go. That will probably be the part that eats up your time the most, but I think you guys have done enough that you won't have too much of a problem dealing with it. Okay, part J, last part. Assume that the heat exchanger has been fixed now by star plumbers Mario and Luigi. However, it is understood that the cache will undergo a phase transition from gas directly to solid when its mole fraction in the gas phase is 0.2. What is conversion when the cache begins to deposit? Okay, so this kind of goes back to almost like mini term 2. That goes back pretty far. So part J, don't make fun of my J's, please. So we said that at a conversion of 0, wait, no, it wasn't a conversion. Sorry. At a gas phase fraction, Y is equal to 0.2. Our cache will start to deposit out of the gas phase into a solid. So I guess we'll say that's YC. So another way we can write that is when it's based off of C, when the mole fraction, oh Lord, there we go. Okay, so that is just the definition of the mole fraction. So we can do it in molar flow rates. That's just fine. So our molar flow rate of C divided by the total molar flow rate, which is just the sum of all of our species, the molar flow rates of all of our species. And we can rewrite this in terms of our initial molar flow rate and the conversion. So going back, we know that FC will be equal to FD naught times the conversion, because it is 1-to-1 from from D to C. Same thing down here. D is going to be FD naught times 1 minus the conversion, and FC naught will be plus FD naught times 0.2x, because it is 1 to 0.2 for D to C naught. C naught, yeah, to C0, not C naught. So now we all know this is equal to 0.2. We know FD naught, and we don't know x. So from there we can solve for x. And that will be the conversion at which we reach a vapor mole fraction of 0.2 of cash in the gas phase, and at which point then it will start to deposit out of the gas phase into a solid. And that just about covers it. I kind of breezed over some of it. Some of it I went a little more in depth on. Some of it I breezed over a little bit. It's because this is, for those of you that are going to take the final, this is a very good homework to do. It'll definitely prepare you for it, give you an idea. I mean, these questions are going to be harder than the ones on the test, but it gives you a feel for the kind of progression that the test could have, the concepts that are definitely going to be covered on the test. And yeah, it's just a great review. And for those of you that are that want to skip the test, it's required that this one be taken. And I guess I could give a couple points on the final. One thing that I'm fairly confident will be on there, because it didn't seem like it appeared on your test, is going to be non-ideal reactors, which was mainly the first two problems of homework 9. I remember that was like the E of T, the F of T, kind of those step inputs of our reactants and concentrations. Outside of that, there will almost certainly be a mechanism. There will almost certainly be some kind of non-isothermal problem on there. It's good to remember those. What else? I would say the majority of what you see on here will likely be on the test. Maybe not so much math heavy. I don't remember if I needed a calculator for the final. But being able to work it out kind of the way I did here, just very all symbolically, that's really what you want to be able to do on this test. I know I think a lot of you struggled with the coding in this class, but that's not going to be on the test, so don't worry. But being able to symbolically solve it, that's really what you want to be able to do. So that just about covers the assignment. I'm thinking this is the last video I'm going to do. The reason for that is I don't really see another reason for making another video for this homework. So Friday will just be Zoom, and Tuesday will just be Zoom for anyone that has questions on the final. And I'm thinking that's just how I'm going to end these office hours. I'll just leave it open for questions for a little bit. If I don't get any, I will end it a little early. I understand that you guys had 2 tests yesterday. You're probably not too interested in doing this homework. That's fine. This video will be up later for you guys to look at. As always, me and Katie will be available for questions throughout the week. And yeah, good luck, guys, on this last homework and on the test for those of you taking it. And I hope you guys don't have to have a semester like this again. It hasn't been fun.